Okay, so now let's get started with our uh, design principles, right? How to design algorithms. So, as I had told you into an introduction class, there is no fixed recipe of designing algorithms, right? But uh, what we are going to learn is just some basic tools and techniques which you can always keep with you, and you can whenever you see a new problem for which you want to design an algorithm, you could try to apply these ideas, and they might help, they might not help, right? So um, but I mean, the point is that these list of ideas will be applicable to a really large number of settings. That's why really we are looking at them. So yeah, so yeah, hopefully you'll find them useful. Uh, so what the first design idea is this idea of going to a subproblem or reducing to a subproblem. So basically what it says is that, so first of all, what is a subproblem? So a subproblem is the same problem on a smaller input, right? So what do I mean by a smaller input? So if your input is an array, then the smaller input could be a sub array, right? So if your input is an array of size n, then by smaller input, I just mean maybe array of size n minus 1 or array of size n minus 2 or even array of size n by 2, right? So that's what I mean by smaller input. Um, in case of a graph, if your input is a graph, then you could consider subgraphs as smaller inputs. So you could delete a few vertices, you could delete some edges, and that gives you a smaller input, right? So basically the idea is that you think of a subproblem, right? So you think of the same problem on a smaller input and assume that someone already gave you a solution for that subproblem, right? So assume that for that smaller input, you already have a solution. Now you think, how can you build a solution for your original problem using that solution for the subproblem, right? Can you somehow um, use some simple tricks, some simple operations, right? Um, Design a simple algorithm which can take that solution of the subproblem and um, come up with a solution for your original problem, right? So that's the first thing you could think about. Suppose you succeed in this, then you come to that question, that how to really solve that subproblem, right? Because no one will really give you a solution for that subproblem. We just assume that that subproblem is solved. Um, but the point is that the idea would be to solve the subproblem using the same strategy again, right? So then that smaller input will become your actual input, and then you try to apply the same strategy on that smaller input, right? So you go to a further smaller input, assume a solution for that smaller input, and so on, right? So that's the basic idea. So basically we are talking about some kind of recursive or inductive strategy, right? um, but the implementation need not be always recursive, so the same strategy you could implement in an iterative way also. So recursive or iterative, whichever is more convenient, you can go with that, right? It's just that uh, it's convenient to think, I mean, just when you are designing an algorithm, it's convenient to think in this recursive manner. And another advantage is that it also useful in analyzing the running time of the algorithm, right? So when you think of your algorithm in this recursive or inductive way, it also makes the analysis easier. So I will um, take a very simple example, and I will say, we'll see how to apply this strategy on that example. And maybe it will be more clear what all I mean by all this subproblem and building a solution for the original problem from the subproblem and all this. But before that, are there any questions?
Sir, isn't it the first constraint to use the divide and conquer strategy? Like if we could divide a problem in subproblems and the subproblems, I mean, all the problems should be solved in same by the same idea. Isn't it the first constraint of divide and conquer?
Right, that is correct. Right, so divide and conquer, you could say is, um, part of the same strategy, right? So here we are saying that you go to a smaller subproblem. So in divide and conquer, you actually go to decrease the input size by half or by one third or something like that. So that's a particular way of going to a subproblem. Yes, and as you said, we should be able to um, s- devise some method to solve our original problem given the solutions for the subproblems. Yeah, but by subproblem, I don't always mean that you go to a input of size half. It could also mean an input of size n minus 1, right? So we'll see some examples, what exactly I mean by this. So any other questions? Okay, so let's look at this very simple example of finding the minimum value in a given integer array. So let's say you have this array A1, A2. The entries are A1, A2, A3 till AN. So the size is n, and we want to find the minimum value among these. So of course you know how to do this problem. Um, um, I just want to describe this strategy using this simple example. So so here, for example, you could consider the size n minus 1 array as the sub, as the smaller input, right? So what would be your sub problem here? Your sub problem would be to uh, find the minimum over the first n minus 1 entries, right? So you could say the sub problem is find the minimum value among the first n minus 1 values. Okay. So suppose someone already gives us this minimum, right? So let me call it mn minus 1, right? So m subscript n minus 1. So this is the minimum value among first n minus 1 values. And now I want to find I want to solve my original problem, which is the finding the minimum value among all n values, right? So let's call it mn. So let's say mn is the minimum among all n values. So can you um, so if you are given mn minus 1, can you compute mn by doing some simple operations? So can you suggest some simple way?
It will be just comparison of mn minus 1 with the an, and
Right,
whichever is smaller, we reassign the minimum value.
right, right.
So
So
taking minimum of mn minus 1 and an.
right, correct. Yeah. So basically, this there is a simple relation between and mn minus 1, which is that the minimum among the n values is nothing but minimum of two things. So one is mn minus 1 and one is an, right? So so this is how we solve our original problem using the solution for the subproblem, right? So in this case, it was very simple, right? But we'll see examples later on when this step needs some thinking, right? That how to build the solution for your original problem using the solution for your subproblem, right? So that step is already done here. So you simply need to find the minimum of mn minus 1 and an, right? So um, I mean, often when you write such relations, I mean, such kind of equation, or I mean, this might not be a simple equation. It could be a small procedure. So proving the correctness of that step is very important for proving the correctness of your algorithm, right? So right now in this example, um, this correctness of this equation is kind of obvious. If it's not obvious, you should think about it, right? That why I'm writing this, why I'm writing that mn is the minimum of mn minus 1 and an, right? So if it's not very hard to see that this equation is correct, and once you prove correctness of this step, then the correctness of your whole algorithm follows immediately, right? So uh, now let me come to the implementation, uh, right? So if you want to implement this idea recursively, what you could do is you could define some function, let's say with name min, and it takes an a input an array a and an index, let's say I, right? So what is it supposed to output? So it's um, supposed to output the minimum value among first I values, right? And so you could recursively design this function. So you could just say that if I is equal to 1, then then you simply output the first entry, right? Because if you just want minimum among the first, I mean just one value, then the value itself is the minimum. And if I is not 1, then you could recursively call the same function for the first I minus 1 values. So you could take output minimum of two things. So one is calling the same function recursively for I minus 1, and so that gives you, so you assume that that gives you the minimum value among first I minus 1 entries, and then you compare it with the ith entry, so let's say ai, and you take the minimum of the two, and that is your output, right? So that's a simple recursive implementation of this idea. And you also, I mean, you also know an iterative implementation of this idea, which is basically um, you could keep a variable m, and so you could initialize as the first entry, and then you just go into a for loop for I equal to n, for I equal to 2 to n, and basically you keep updating m by taking minimum of the current value of m and the next entry of the array, so ai, right? So that's it, right? So essentially both the algorithms are using this same idea that once you know the minimum value among the I minus 1 entries, you can compute the minimum value among the first I entries, right? And the same idea is here it's implemented using recursion, and here it's implemented using iteration, right? Yeah, so this simple example shows you how to apply this sub-problem idea in this very simple setting. And in the next lecture, we'll look at some more sophisticated problems. So we're out of time, so maybe I should already tell you about this. So this question you could think about is, suppose in an array you want to find both minimum and second minimum, right? So how will you do that? So you can think about it. So there are some obvious ways of doing it, and can you do some faster? Can you design some faster algorithms as compared to the obvious algorithms, right? So you can think about it, and we'll discuss it next time. Yeah. So any questions so far?